The operations of real matrices are also applicable for complex matrices, although there will be some added steps in some. Check them here in numerical solutions to see problems. The premise has two complex matrices A and B, both of order 3. We are to find the conjugates and the transjugates in order to determine A bar times B Hermitian and A Hermitian times B bar. First, we need to look for the conjugates. This operation is simply the sine inverse of the imaginary numbers in each element. So taking matrix A bar would have negative 3i for element 1, 1. Element 2, 1 would turn into 4 minus I, and the other elements would have been transformed similarly. The conjugate of matrix B is work the same thing, making element 1, 1 as 1 plus 2i, but element 2, 1 remains as 3, as this is a real number. For the transjugates of the matrices, take the transpose of their conjugates. So the elements negative 3i, 5, and negative 1 minus 6i, which are from the first row of matrix A, become the first column on A raised to h. This is the same with the transjugate of B, where the row elements 1 plus 2i, 2i, and 4i become the first column of matrix B raised to h. The first multiplication is A bar times B Hermitian. Since both matrices have complex numbers, one should be familiar with multiplying complex numbers using the FOIL method. Start with element 1, 1, which includes negative 3i and 1 plus 2i. They will be multiplied as negative 3i minus 6i squared. I squared is actually negative 1, simplifying the product into 1 minus 3i. Add the next pair, which includes 5 and 2i. This pair is multiplied into 10i. And yet add another pair with negative 1 minus 6i times positive 4i, which make negative 4i minus 24i squared, simplified as 24 minus 4i. Add the three pairs to get 30 plus 3i. This is element 1, 1. Element 1, 2 starts with a pair negative 3i and 3, which are multiplied to negative 9i. The next pair has 5 multiplied by 2 minus I, which gives 10 minus 5i. The last pair includes negative 1 minus 6i and 5 minus 3i. They are multiplied as negative 5 plus 3i minus 30i plus 18i squared, which is then transformed into negative 1. Add all three pairs to get negative 13 minus 41i for element 2, 1. For element 1, 3, the pairs are taken from the first column and the third row. This starts with negative 3i times the element 4 minus 3i. They become negative 12i minus 9i squared. That is, negative 9 times negative 1, thus the product is 9 minus 12i. The second pair includes 5 and 4 minus I. Distribute 5 to have 20 minus 5i. The third pair has negative 1 minus 6i, with 1 minus 2y, giving negative 1 plus 2y minus 6i plus 12i squared, which can be simplified as negative 13 minus 4i. Add all three simplifications to get negative 2 minus 21i. After finishing the first row, we move to the second, starting with the first column. The first pair has 4 minus I multiplied by 1 plus 2y, giving 4 plus 8i minus I minus 2i squared. This is simplified as 6 plus 7i. The second pair has 3 minus 2y multiplied by positive 2i. This is simplified as 6i minus 4i squared, which can be converted into 4 plus 6i. Then there is 7 plus 2y times positive 4i, which gives 28i plus 8i squared, reduced to negative 8 plus 28i. Add the 3 to make 2 plus 41i. This is element 1. The next element to consider is that for A22, which is solved with 4 minus I times 3, which is 12 minus 3i. The other pair for the element has 3 minus 2y and 2 minus I, expanded as 6 minus 3i minus 4i plus 2i squared. All four terms can be taken as 4 minus 7i. The last pair for the element contains 7 plus 2y and 5 minus 3i, expounded as 35 minus 21i plus 10i minus 6i squared. That is taken as 41 minus 11i. Add all three to get 57 minus 21i. Moving to the third element in row 2. The first pair includes 4 minus I times 4 minus 3i, making 16 minus 12i minus 4i plus 3i squared, giving 13 minus 16i. The next pair has 3 minus 2y times 4 minus I, that is 12 minus 3i minus 8i plus 2i squared, simplified as 10 minus 11i. The last pair comprises of the element 7 plus 2y and that with 1 minus 2y. They turn into 7 minus 14i plus 2y minus 4i squared, which can be reduced to 11 minus 12i. Add the three products to get 34 minus 39i. This element completes the second row. The third row has the first pair as 2 plus 3i with 1 plus 2y. They give the product 2 plus 4i plus 3i plus 6i squared, which can be reduced into negative 4 plus 7i. The second pair has 4i with 2y, giving 8i squared. This is transformed as negative 8. The third pair has 5 minus 3i with 4i. The product is 20i minus 12i squared, which is taken as 12 plus 20i. Add all three to get 27i. For element 3-2, we start by multiplying 2 plus 3i with 3. This gives 6 plus 9i. The second pair has 4i times 2 minus I, which make 8i minus 4i squared, and be transformed into 4 plus 8i. The third pair has 5 minus 3i times another 5 minus 3i. They are multiplied into 25 minus 15i minus 15i plus 9i squared, which makes 16 minus 30i. Add all three products to get 26 minus 13i. For the last element of the matrix, we start with 2 plus 3i times 4 minus 3i to get 8 minus 6i plus 12i minus 9i squared. That is 17 plus 6i after reducing. The next pair has 4i with 4 minus I, and that is 16i minus 4i squared, or 4 plus 16i. The last pair has 5 minus 3i and 1 minus 2i. That would be 5 minus 10i minus 3i plus 6i squared, which makes negative 1 minus 13i. Again, add all three products to get 20 plus 9i. This is the completed A bar times B Hermitian. Let's also determine the product of A Hermitian with B bar. By starting with element 1, 1, we have negative 3i times 1 plus 2i. That is negative 3i minus 6i squared, which is then taken as 6 minus 3i. The second terms are 4 minus I multiplied by 3, making 12 minus 3i. The third has 2 plus 3i times 4 minus 3i. That would be 8 minus 6i plus 12i minus 9i squared, simplified as 17 plus 6i. Take the summation of the 3 to get 35. For element 1, 2, we take the first row and the second column of the respective matrices. That would be negative 3i with positive 2i, giving negative 6i squared, or positive 6. The next pair has 4 minus I with 2 minus I. That would be 8 minus 4i minus 2i plus I squared, simplified as 7 minus 6i. The last has 2 plus 3i and 4 minus I, giving 8 minus 2i plus 12i minus 3i squared. This is also simplified as 11 plus 10i. Adding the three simplifications, we get 24 plus 4i for element 1, 2. The next element starts with negative 3i and positive 4i, giving negative 12i squared, or that is 12. The second pair has 4 minus I times 5 minus 3i, giving 20 minus 12i minus 5i plus 3i squared, simplified as 17 minus 17i. The last pair contains 2 plus 3i times 1 minus 2i, multiplied as 2 minus 4i plus 3i minus 6i squared, which is simplified to 8 minus I. Add all three products and get 37 minus 18i for element 1, 3. From the second row, we start with element 2, 1. The first pair to solve this is 5 with 1 plus 2i, simplified as 5 plus 10i. The second pair includes 3 minus 2i and 3, multiplied as 9 minus 6i. The third has 4i times 4 minus 3i, multiplied as 16i minus 12i squared, which is also taken as negative 1, so element 2, 1 becomes 26 plus 20i. The next element 2, 2 has the first pair as 5 times positive 2i, which is 10i. The second pair contains 3 minus 2i and 2 minus I. These are multiplied into 6 minus 3i minus 4i plus 2i squared, simplified as 4 minus 7i. Completing the products for the element, we have 4i times 4 minus I, which shows 16i minus 4i squared. This is also 4 plus 16i. Add all three products to get 8 plus 19i. The last element for the second row starts with 5 times 4i, which is 20i. The next pair has 3 minus 2i multiplied by 5 minus 3i, resulting to 15 minus 9i minus 10i plus 6i squared, which turns into 9 minus 19i. The last pair contains 4i with 1 minus 2i. That makes 4i minus 8i squared, or 8 plus 4i. So adding all three products, we get 17 plus 5i for element 2, 3. And that completes row 2. Start row 3 with negative 1 minus 6i and 1 plus 2y to have negative 1 minus 2y minus 6i minus 12i squared, or 11 minus 8i. The next pair has 7 plus 2y with 3, multiplied as 21 plus 6i. Then this is followed by the last pair, which has 5 minus 3i times 4 minus 3i, multiplied as 20 minus 15i minus 12i plus 9i squared. 11 minus 8i plus 21 plus 6i plus 11 minus 27i gives 43 minus 29i. For element 3, 2, we start with negative 1 minus 6i times 2i, which is equal to negative 2i minus 12i squared, or 12 minus 2i. The next pair has 7 plus 2y times 2 minus I, giving 14 minus 7i plus 4i minus 2i squared, simplified as 16 minus 3i. The last pair contains 5 minus 3i and 4 minus I, which are multiplied to get 20 minus 5i minus 12i plus 3i squared, simplified as 17 minus 17i. So if we add 12 minus 2y to 16 minus 3i with 17 minus 17i, we get 45 minus 22i. The last element can be solved by taking the product of the first pair, negative 1 minus 6i and 4i. That is negative 4i minus 24i squared. This is then simplified as 24 minus 4i. The next pair has 7 plus 2y times 5 minus 3i, which gives 35 minus 21i plus 10i minus 6i squared. This is simplified as 41 minus 11i. To complete the element, we also multiply 5 minus 3i with 1 minus 2y. That would be 5 minus 10i minus 3i plus 6i squared, simplified as negative 1 minus 13i. The products are added to have 64 minus 28i. Now, matrix for Hermitian A times B bar is completed. To summarize, A bar times B Hermitian has the elements as solved, and if you would also try to work on the product of B bar with A Hermitian, the following elements are the results. Comparing the two matrix products, you can see that the main diagonal elements are still the same. The other pair has similar case. The main diagonal elements of A Hermitian times B bar are the same with the other product B Hermitian times A bar.